Hi everyone, I just wanted to do a video on, or just kind of reiterating when we accept and when we reject the null hypothesis. This week we were doing a very simple concept of when we're comparing or statistically inferring a sample mean to a true population mean. In this case, we either know the population mean or we don't and we're trying to estimate it. Okay, so a lot of times in statistics, we only have a sample to draw conclusions from, and so that is how we are able to estimate a true population mean. But that's the whole point of statistics, is to use samples to give us more information about a given population. So I have poorly drawn this line. It is not horizontal, but this is going to represent our population distribution, which we always say is normally distributed. Okay, so in a perfect world, this would be a symmetrical curve. In our sample, which is what we have collected, we're going to assume we have a normal distribution. Obviously, we have no data, so it's kind of hard to argue this with no data, but in a given situation, we would say we've calculated our z-score of skewness and kurtosis, and we can accept that this distribution is relatively normal. So that allows us to infer information onto our population. So I'm using an example of a 95% level of confidence. That's going to be the most common one that we use in this class, but there are going to be instances where for the sake of example and practice, you might be using a 90 or a 99% level of confidence, in which case some of this information might change a little bit. But with this information, we know the level of confidence is going to represent the area under the curve that is including a given confidence interval. So when we define what this level of confidence is, that provides us information about locations with regards to whatever units this distribution is in, right? That gives us an idea of locations of where our confidence interval boundaries will be, such that 95% of the data is between whatever these two values are, okay? Based on our percentages of between the distribution, since we have a two-tailed test, we're going to have two regions of rejection, or two areas of error that we're calling alpha, right? And we find this by 100% minus whatever our level of confidence is, and then if it's a two-tailed, we divide that value by 2 and write it as a decimal, okay? So in this case, alpha would be 5%, right? Because 100 minus 95 is 5. So 5% divided into 2 tails is going to show us that the area under the curve to the right of the mean is 2.5%, and the area under the curve to the left of the mean is 2.5%. Now remember, we present alpha as a decimal value between 0 and 1, so we would actually say this is 0.025 and 0.025. So when you look this up on the Z table, right, I like to go off of this lower end because it's easier to look up, but you're looking for a value that is close to 0.25 or as close to 0.25 as you can without overestimating. So the reason being, let's say this area is here. If you overestimate by a little bit, that means you're including a good portion of the population that, or not a good portion, but at least possibly including some people who may be in the regular confidence interval. And so if we underestimate, we're actually being a little bit more precise in terms of making it more difficult to reject the null hypothesis. So this is how we get our alpha values, right? At those given alpha values or areas, we end up getting z-scores. So in this situation, z is going to be equal to negative 1.96 and positive 1.96 because we have 2 tails, right? So once you figure out one side, you know the other side, okay? these lines, right, whatever the value is of the units of this distribution, so say we're measuring height, right, the units of the interval would be in inches. But we have a particular value that occurs at negative 1.96 and a particular value that occurs at positive 1.96 z-scores from the mean. So this side is going to represent the lower bound of our interval, and this side is going to represent the higher bound, or the upper bound. Okay, so when we put these two together, we can then, oh no, hold on a second. Things are moving. Okay, we can then say this is our confidence interval. Okay, so I'm gonna put this in yellow, right? And remember, we represent the confidence interval in brackets, which means we're including both the value that exists at the lower bound as well as the value that exists at the upper bound. Now, what does this mean with regards to accepting or rejecting the null? Okay, remember, all of this information is going to be estimated based on the concept or the assumption that you have a normal distribution in your sample. So what we're really doing, if we're comparing population mean to sample mean, right, we're looking at where is the location of the sample mean in relation to the mean of the population. Okay, if the sample mean lands anywhere within our confidence interval, okay, so let's do some arrows. Okay, let's say anywhere in this bracket, the sample mean lands somewhere in this area according to where the population mean would be. We're going to say P is greater than 0.05. Therefore, we accept the null hypothesis, meaning our sample is representative enough of the population or the majority of the population that we can accept that this sample is the same as the population it came from. Okay, so I'm going to do this in orange just so we have some distinction. Okay, remember 0.05 is going to be, again, the total region of alpha, or the total region of error that you're willing to accept. So if we have a large degree of potential error, right, then we're going to say, well, I'm not too sure that this sample is actually different from this population. Okay, so when P is greater than 0.05, that means your sample has landed somewhere in this 95% area of your population, or estimated population distribution if it's unknown. Okay. In a different situation, now let's say our sample mean lands somewhere over here in the distribution of sample means for our population, right? So when we have two-tailed, right, it can land on this side or it can land on this side. Okay, we know there's a difference, we're just not specifying what the difference is. So in this case, right, landing outside of our confidence interval, this is when we would reject the null, right? Or this is the regions that we would say the research hypothesis is true. And we again still evaluate this off of the null hypothesis. So when P is less than 0.05, that means we have a low probability that we made an error. Okay, so if you think you are pretty certain or have a low chance of error, you're probably going to accept your results or your statistical results and say, I have a significant difference between sample and the population, right? Whatever you collected here, this sample representation is different enough from the population that we could say they actually belong in a different population, right? Or there's something that has been administered to this sample that makes it different from the population, okay? So in this case, this is when we reject the null, okay? And this is true on both sides of the mean in a two-tailed test. Okay, so I'm going to put these in pink, just so we've got some distinction. Okay. And I like colors, if you guys haven't noticed from lectures, so we got to make it pretty. Okay. So hopefully this drawing kind of helps make a little bit more sense on how we infer sample information to population information. And it's not always going to be that you're predicting a mean of a population from a sample, right? It doesn't always have to be a mean. Sometimes this is going to be a mean difference. So if you're comparing two different groups to each other, you're saying this is the mean difference that we got between groups 1 and 2. How would that relate, or how would that be estimated in a population? And then in this case, this would represent the confidence interval for the expected mean difference, or the estimated mean difference for a given population. So that's when we do intervention type studies, and we're comparing a control group to an experimental group. We can say if the experimental mean is different enough from the control group mean, right? The mean difference is going to be larger. Therefore, if it's large enough that it lands in this area, or that we get a p-value less than 0.05, same thing on this end, right? Then we can accept that that experiment was effective, right? That our control group and our experimental group are different enough that they could be considered to be collected from different samples. So that's a kind of crossover concept that we're going to get into in t-tests and ANOVAs, but this general layout is going to be the same, right? You're just going to kind of change what the units are on the axes here. Okay, so hopefully that helped make a bit more sense. Obviously, if you guys have questions, please let me know.